to feed this model. We're going to feed this model with biosignals that are directly recorded on the subject. So we're going to record EMG signal to get muscle activation and joint angle to update the kinematic state of the muscle, the model, and the muscle model. And to get access to this kinematic state of the muscle model, so mainly the muscle tendon length, but also the movement arm of this muscle, we use a surrogate stage that is based on spline to compute from joint angle, moment arm, and muscle tendon length. But what is very important, since we're recording and using biosignal from a user, you need to kind of calibrate, to personalize this model to the user, so that the estimated joint torque that you computed, but also estimated muscle forces, are really the one of the subject. And for this, we have a calibration stage, which is based on an optimization routine, where we're going to basically reduce the error between the estimated joint torque and the experimental joint torque computed from average dynamic by changing the muscle parameter to better fit the one of the user. So for example, in this video, we can see the framework, so the graphical user interface on the screen. So we can display so EMG signal, muscle forces, but also the estimated joint torque. And we also have a skeletal model that is updated with the kinematic state of the subject. So we can see it here on the treadmill, the subject that where we are recording currently EMG signal. We're computing joint position from marker data. So we also have a real-time reverse kinematic framework to get this joint angle in real time. But we also have, so the estimated joint torque from our model, but we are also running a real-time reverse dynamic framework because we also have access to ground reaction forces using this treadmill that you can see here. So we developed like this kind of easy to use graphical interface. At least for me, it's easy. For some master students, it's less easy for them. And we have a real-time system that has total delay. So from EMG to joint torque of under 34 milliseconds in average. And this is very important because we want to be under the electromechanical delay, because this means that we can compute joint torque and muscle forces before it happens within the subject. So before the subject realize and contract their muscle to produce forces, we already have this information. This is very important because it gives us a windows where we can use rehabilitation controller to provide rehabilitation into the subject before these forces really happen. Then we also looked at the joint torque that we estimated. So here on this graph, we can see in blue the estimated joint torque from our framework, and in black the inverse dynamic torque. And what is interesting is that we are able to compute joint torque on tasks that were not used for the calibration. So we can extrapolate on new tasks. So for example, we calibrated on gait, squats, or calf rise, and we are able to estimate joint torque on jumping, side step, and so on. But also we can estimate joint torque on unknown degree of freedom. So we calibrated on knee flexion extension or ankle plantar dorsiflexion, and we are able to estimate joint torque on the ankle subtalar-flexion, for example. So we are calibrating this muscle on degree of freedom that were not used, that were used for calibration, but we can still estimate on the same muscle if other degree of freedom. So that is very interesting when you want to provide assistance via wearable devices on each subject during working or all kind of tasks. So now that we have this kind of real-time framework, how can we use it to control robotic devices and interface with them? So that was the next step in our study. So we use an exoskeleton that is applied to the user, and we provide mechanical assistance. So we have a low-level torque controller that is going to take this estimated biological joint torque from our framework, multiply it by a support ratio, and provide this as mechanical assistance via the exoskeleton. So here in this video, we did some experiment on stroke and spinal cord injury patients, where we asked them to follow, to track a joint position that was displayed on the screen. And we did that for two levels of assistance, so like a low level of assistance, where we were providing 10–20% of the own biological joint torque back, and a higher gain where like around 50%. So what we saw is that, first of all, since we were putting exoskeleton on patients, we wanted to see, okay, can they at least finish the task? Because that's where patients, so most of these patients came, like, for example, in wheelchair for the spinal cord injury patient. So we were not sure if, even with an exoskeleton, they're able to finish the task, and they were able. And what we also saw is that by changing this level of gain or assistance, we were able to modulate EMG level, mainly by increasing the gain. So here on this plot, we can see on the right low gain, on the left side the high gain. We can see that by increasing the assistance, we were able to decrease EMG. So we were able to modulate the EMG of the patient. But also very interesting is that we were also able to modulate the EMG variation. So we were able to make the EMG pattern of the subject more reliable and more repeatable over tasks. So for the same task, the patient were able to provide EMG that were less variable. So that was very interesting for us on patients, but that was only for seated exercise. So then we also looked at, okay, can we also assist during walking? So this time on healthy. So we tried two different conditions. So one was the exoskeleton providing assistance using our framework, and the other one was a minimal impedance or transparent mode from the exoskeleton, where the exoskeleton tried to be as transparent as possible to the user, so trying to compensate his own effect on the user. And we did that on different walking tasks, so 2 different speed and 3 different elevation on a treadmill. And what we saw is that, so for all the tasks that we recorded, so the 2 different speed and 3 different elevations, we were able to reduce EMG levels. On plot, we can see in purple the minimal impedance, transparent mode, and in blue when we assist via our framework. So we can see that for all the tasks, we were able to reduce EMG, so which was great. But what was very important is that we could also reduce EMG levels, so providing positive assistance also during this transition, during those tasks. And this is very important because currently control of exoskeleton, or like the state-of-the-art controller, they use state machine. So they can only assist during some predefined states where they know which kind of torque patterns they have to give back. But during the transition between those states, they don't have an optimal torque pattern assistance, so they cannot provide positive assistance. That's using our framework, since we are continuously computing joint torque, we can continuously assist the user. We also have the same effects on joint torque, so we were also able to reduce biological joint torque. So here in darker shade, biological joint torque for all tasks, also during the transition. But what was very interesting is that if you take this biological joint torque, so in this dark shade, and on top of it, you add the interaction torque between the human and the exoskeleton, which is in lighter shade, then you can see that the total torque to realize the task was similar between the 2 conditions, which means that basically the subjects were reducing is almost all forces by the same level of assistance was providing. So this means that we can modulate the muscle forces and joint torques that the subject is doing by providing this assistance that is totally accepted by the user. So that was very interesting, and I think that can be extremely interesting also for rehabilitation, when you can really modulate muscle forces and have the subject really accepting this assistance that we are providing via an exoskeleton. So we also did some single case study on higher dexterous tasks, so mainly moonwalking, because we did this task on walking, where even if it was different inclination on speed, it was still very similar. So we looked at a more difficult task to assist, which is moonwalking. And also for this task, we were also able to reduce EMG level for considered muscle. So we also looked at control of prosthetic, because we were thinking, okay, can we bring this advantage to also control of prosthetic, since we just have to change the model used. So we use an hand prosthetic, we change our model for upper limb model, and we changed actually the way the calibration was done, because we didn't have access to embedded dynamic, because the hand of the subject was non-existent anymore due to amputation. And then we interfaced it so with this commercial hand prosthetic, and use the same idea of using biological joint or multiplied by support ratio to give assistance. So we did two tests. One was asking the subject on the screen to control a cursor to go to point A to B by controlling flexion, extension, and rotation of the wrist, and also to move clothespin from point A to point B as fast as possible. And what we saw is that the subject was able to control multiple degree of freedom continuously and volitionally. And you can see it here that to go to point A to point B, he took the shortest path using 2 degrees of freedom. But we also saw that we, using our framework, we can move clothespin to point A from A to B faster than the classic and commercial controller that is sold with the prosthetic. So mainly using 2 electrodes and a proportional control from it. So then we did all this in vivo study, but there is some issue and difficulty with in vivo studies. So we also now looking at, okay, can we simulate in silico this human-machine interaction, and can we better understand it? So the motivation is that in vivo studies is limited. So it's limited in time. So we cannot like record for days and provide assistance for days currently with an exoskeleton. And we also are limited on the number of internal variables that we can look at because using our framework, for example, we need to record all EMG, the EMG of all muscles that we want to look at. So that's not really possible. That using in silico study, then you can look at 100 of muscles for the back. You have to look at 100 of muscles. One of the difficulties is the control of the neuromuscular model. So how can we control in silico this neuromuscular model since we don't have a subject? So what we are looking at is to emulate the central nervous system, mainly using neural network. So to train this neural network, we need to have access to a simulation of the neuromuscular system. And the best and state-of-the-art solution for that is OPENSIM, which is very precise. So it's one of the best biomechanics software out there. The problem is that it's precise but slow. But if you want to train on a network, you need to have something that is fast because you need to have a lot of repetition to train this neural network. So that's why with some colleagues from Meta AI, we developed the MyoSuite framework, which is a very fast simulation of the neuromuscular system, which is, for example, it is currently 100 times faster than OPENSIM for computing muscle forces. But the question is, okay, how far are we from OPENSIM in our neuromuscular system? So to getting closer to it, what we use is an optimization routine where we try to kind of fit the muscle forces from our model, from the one in OPENSIM, by changing kinematic and dynamic parameter in our model. And what you can see here on this graph is in blue, the muscle forces from OPENSIM, and in green, after this optimization routine, that we can kind of imitate the muscle forces from OPENSIM quite closely. So then once we have this this simulation working, we try to train our neural network using reinforcement learning and to find the best policy possible using natural policy gradients on different tasks. So we look at finger reaching. So we had these two models, so model of the wrist and hand, and model of the elbow. So we look at, can we control the elbow? Can we control finger? Can we reach the finger? We also looked at more difficult tasks such as turning a key, moving a pen, or moving two balls inside our hand. And what we saw is that, okay, it is possible to train this policy, but some policy, like for example, moving the ball, take more than 70 million samples to get something successful. So that's why it's really important to have extremely fast simulation so that you can train this neural network that needs a lot of samples. So then we simulated an exoskeleton. So we simulated an exoskeleton using the controller that I presented before. So we basically gave back the estimated joint torque with a support ratio back as assistance. And we tried that on 3 different conditions. So the first one was the healthy model. Then we also implemented a sarcopenia model when we reduced muscle forces by 50%. So the Fmax is the muscle model by 50%. And a fatigue model where Fmax was reducing over time depending on the loading that was applied on the muscle. So we asked the model to try to sustain a 90-degree angle. So using the LC model, we can see that the model without exoskeleton and with exoskeleton is able to sustain this joint angle. And then when you start using a model with sarcopenia, you can see that without the exoskeleton, the model has trouble to sustain this angle, that with the exoskeleton is getting closer to it. And it's even more visible when you have the fatigue model, that you can see that over time, the model is not able to sustain this joint position, that with the exoskeleton is more able to sustain it. And this can be seen also with the muscle activation of the model. So you can see that with the exoskeleton, we can reduce EMG activities as well as muscle forces. And that is in line with the in vivo study that I presented before. So this software, this MyoSuite software, is currently open source. And we have, with our colleague from Meta, we created this MYOCHALLENGE, which is going to be presented at the NeuroMusculoskeletal conference. So if you're interested in AI and neural modeling, you can join this challenge where you would have to try to have a model learning to roll a dice or to move ball inside our hand. And the prices for this challenge is up to 20K for the best team. So that's basically the end of the talk and the end of my time also. So what we saw is that we can create a real-time neural models that can control the skeleton. And using this model and this controller, we can modulate EMG, muscle forces, and joint torque, which I think in the future will be extremely important to provide personalized rehabilitation. We also show that we can have fast simulation of the neural system that can be used for training policy for neural network or AI for fine manipulation. And that this exoskeleton that we can simulate in this neural model that is controlled by this policy produce results that are kind of in line with in vivo study. So that was it for me today. So I want to thank my colleagues and finance that we received for making this work possible. And if you have any question, you're welcome to ask.
Thank you, Guillaume. That was a very interesting talk. Do we have any questions here, or we have one question? You can, if you're not loud enough, I can repeat. Yeah. I'm not sure.
Okay. Thanks, Guillaume, for the talk. I would like to know one thing. So in this simulation model that you use and use also AI, can you address a bit if we can use it for hybrid control? So reducing the number of electrodes, for example, in order to predict in a better way the force that you want to generate and the assistance that you want to generate in case you use the wearable system or understand.
Was that clear?
Kind of. So the question is about if we can use this framework, so this MyoSuite framework, to reduce the number of EMG for control of exoskeleton, I think.
Yes, it was.
Yes.
Okay. In the long term, I want to say yes, because you can train this policy to kind of control a lot of different movement and so on, and find out some muscle activation to control, for example, the neuromuscular model. But there is some limitations. So the first one is that you need to know what the subject wants to do, so that you can ask the policy to try to do the same. So at the end, you need to know what the subject wants to do, which is extremely difficult. And the second one is that right now we are trying to look at, okay, is the predicted activation close to the one of a real subject? So is the predicted activation natural looking? And for now, it's not really natural looking. So I will not expect that you could merge this activation with real activation right now, but we are working toward it. But there is other solution that I think are maybe more interesting if you want to reduce the number of EMG. So you could look at using synergy, for example. So you can predict muscle activation using synergy from other EMG, real EMG, or using, so for locomotion, reflex-based muscle activation prediction.
That's okay?
Yeah.
A quick one, if I think Heike raised hand. Did you have a question, Heike?
Yes. Yeah, I'm wondering what the target group is. You mentioned for the fine motor manipulation tasks. You mentioned sarcopenia, but that means that people have lost force, but you don't need that much force for these fine manipulation tasks. So who would benefit?
So, I mean, I won't say for now, nobody will benefit for it because it's very early work. For me, in the long term, I think we could look at, for example, the stroke population. I think that would be interesting to look at, or spinal cord injury subject. But the current implementation, so with fatigue and sarcopenia, are more, in a way, proof of concept than really trying to solve issue, because we developed this MyoSuite framework and also added this AI policy on top of it. But we are quite far from something that can be used right now for rehabilitation. But the long-term goal would be to really having this policy that could imitate neural injury, so it can be stroke, it can be aging, and also having model, so muscle model that also imitates so aging and so on. And then you could look at long-term effects on these states on the neuromuscular system, and use exoskeleton to try to counter it. So that would be the long-term goal, but right now we are far from it. So
thank you.
Maybe you can ask a question in 5 years, maybe, and I will have a better answer.
Thank you. It's already very impressive, the fine manipulation it can achieve. It looks really nice.
Yeah, thanks.
Okay, so then we'll move to the next speaker. Let's just thank Guillaume for his talk.